Hello everyone, welcome to the demo of our system which is Refinement Acting Planning and Learning Engine using operational models. So this is how the interface is. So you can select domains which are like you have 5 domains already available, and you can also create your new domain which we'll see later on in the demo. So let's say you create one domain and there are different acting engines available. So uh, the purpose of the acting engine is to carry out tasks that come from the user, and this is non-trivial because the actor needs to handle dynamic events, concurrent tasks, dead ends, and it may have to sense different kinds of information from the environment. Also, the actors may need to collaborate and maintain a task agenda and so on. So for acting engine, we have two possible choices. First one is Ray and the second one is Ape. So once you select the domain and acting engine, you have to select the problem which you define on your own. We'll see later on how we define problems. And then for planning, there are three possible planners that we have, which uses operational models, and also you may not even choose to use the planner. So let's choose UPOM for now and time limit for the planner. Because our planner runs online, we may have the planner stop after a certain um, short interval of time. So let's say we have 5 seconds for the planner. And utility is the parameter that the planner optimizes. So we have three different choices of utilities. You can also define your own utility function. First one is efficiency, which is basically the reciprocal of the cost. So you want higher efficiency, which corresponds to lower cost. So let's choose efficiency here. And learning strategies, we have three different learning strategies, and we may not even do learning. So let's just run a simple example. So as you can see here for problem one, the task is that the robot needs to fetch an object O1 and the result is success. There were no retries, like the robot succeeded in the first attempt, and the utility is the reciprocal of the cost, which is 0.066. And here on the right, you see that the robot is already in location 1. It perceived location 1 and it has picked up location 1. Also, what you can see is the acting tree, which shows that how the refinement takes place. So for each task, here the root task is fetch, and there may be several possible refinement methods. So here it chooses the fetch method 2 for refining the task, and after choosing fetch, it refines into a subtask called search, for which the actor uses search method 1. The search further refines into move and perceive action, which is executed via the execution platform. In the fetch domain, it's just a basic simulator. And finally, it takes, so it's like pickups the object. The move can further be refined into non-emergency moves. So there are two kinds of moves in this domain. One is if the robot needs to go to an emergency location, or it may uh, have to move to a non-emergency location. And this finally refines to this action move. So now let's see, before going into other configurations and running the system, let's see how you define a domain and a problem. So here is a sample domain file. So it will have an actor, an environment, and some uh, the state information. So this state is the variables where the variable is like a object which has Python, um, which is a Python class with variable binding. So basically a dictionary, and it there is a set of rigid variables which do not change with time. So first, in the domain, we need to declare the tasks. So in this simple fetch domain where a robot is moving around, searching and picking up objects, and the robot can carry a limited amount of charge, the tasks are search, fetch, recharge, move to emergency, and non-emergency move. And for each of the tasks, there may be refinement methods, which are programming procedures that give different ways for accomplishing the task. So for search, there are two refinement methods. For fetch, there are two refinement methods. Similarly, for recharge, move to emergency and non-emergency move. So emergency here is notice that it is not a task; it is an event. So it's not something that the user wants to do, but it is something that has happened in the environment, and the actor needs to take care and recover from it. So there may be that the search space is too large or too deep, so you may not have sufficient time to plan. So for those cases, we also support heuristic functions, so that after looking at uh, limited horizon, you can estimate the remaining utility for accomplishing the task using a heuristic function. Now, there we declare all the commands, which are the low level actions, and each can have a programming procedure. So fail is a simply returns failure, and take picks up the object, puts down the object. So the main thing to observe here is that you can put any programs within the commands or actions. And for refinement methods, this is the interesting part, that it can again be any programming procedure which further refines into subtasks, like recharge refines into subtasks, move to after doing some after having some control structure, and then it performs the charge and takes the charger. So similarly, each of the refinement method is a programming procedure. Now here, the environment is very simple, but it need not be in the domain, in any domain. The environment may be complex, but the thing is, there should be some way to simulate the command. So here, it's a very simple simulator where the actions have probabilistic outcomes, and the planner samples an output from a probability distribution. But it can be any sophisticated robotic simulator or any simulator that the user may have access to. So this was how one should define a domain. And for the problem, one thing that the actor needs and is how much time the actions should be simulated. But this is just for a simulation purposes. It's not really something that's needed for computation. Next, for a problem, one should assign state variables. So here there are 4 locations and they are connected to each other. An initial location of the robot, the what charge it is carrying, the load, and the position and of the charger and the object, the containers, like which object is placed where, which robot is handling emergency, and which locations are viewable. So the task here is that at time 3, the task arrives, which is fetch, and the parameters are R1 and O1. So R1 needs to fetch object O1. Now let us go back to our system and see and run for different configurations of actor and planner. So again, let's look at the fetch domain. Let's choose the acting engine as Ray. We already checked for problem 1. Let's check for a different problem. First let's check whether when there is no acting. So in this case, there is no, sorry, there is a check for reactive actor where there is no planning, and time limit, it doesn't matter. So utility is efficiency, and learning strategy also nothing. So let's run. So here you see that the emergency task or sorry, emergency event succeeded with the utility 0.25, and the fetch task utility 0. So fetch resulted in failure. Now let's see after with what happens when we run this with the planner. Say the planner is chosen to be UPOM, and let's run again. So here check that the planner, the actor had to wait for some time, but finally it succeeds with utility of some real number, not 0. Um, so we can also run this with a different utility function. Let's say we want to do success ratio, and let's see what happens. So in this case, the utility comes out to be 0.05. And finally, the robot is succeeding in both the tasks. Now let's not use the planner. Let's use a learning strategy, say learn M. And let's see what happens. So in this case, it used some learn model to choose the best method instead of instead of getting the advice from the planner. So here, again, the robot is able to succeed in the task. Now let's see for some other problem. Say problem 51, we use the planner and say we again optimize the efficiency. So in this case, it's able to succeed and with a utility of 0.048. Let's test for another problem, problem 114. Here there are two uh, tasks. First one is an emergency, second one is a fetch. So the emergency succeeds, but the fetch is failing. Let's see what happens if we do success ratio. So here the emergency fails, but the fetch task succeeds with some positive utility. So this way you can select any of the domains, test domains, and any of the acting engines, Ray or Ape, and any problem that you define. There are three possible planners, or you may choose to act reactively. The planner can be given a certain time limit in seconds. You can optimize different utility functions, use different learning strategies, and see how the acting, planning, and learning with operational models work. Thank you.